because it is the directions are opposite, so we take minus E to the delta. And now we go to the dimension D to A. So D to A, that is belonging to two medias, different medias, and it is symmetrically separated. So here the portion is confined to medium 2 and the remaining is confined to medium 1. And when we go to the directions, here this direct dimension is parallel to the normal components, and when we go to and the directions are similar, looking similar. So we take positive. So from D to A, first half portion is confined to the medium 2, so we take positive E to N, and it is extended to delta H by 2. And the remaining portion is confined to medium 1 and it is extended to delta H by 2. So we take positive E1 and delta H by 2. So total, and according to the Maxwell's equation, the total field intensity is equal to 0. Now we will consider, so minus E1 and delta H by 2 plus E1 and delta H by 2 plus E2 and delta H by 2 minus E2 and delta H by 2. So finally we can write E1t minus E2t into delta W equals to 0. Here from this delta W cannot be 0 because it is the dimension, so it cannot be 0. The remaining is so here delta W cannot be 0. Therefore, we can write E1t minus E2t is 0. And from this, we can write E1t equals to E2t. E1t equals to E2t. It means that here this is one of the boundary conditions that shows that here the tangential component of electric field intensity is continuous across the boundary, across the interface. From this, we can conclude that tangential component of electric field intensity is continuous across the boundary. And we know that since D1 equals to epsilon 1 into E1t and D2t equals to epsilon 2 into E2t. So we can write here E1t is simply D1t by epsilon 1. Therefore, D1t by epsilon 1 and D2t by epsilon 2. And from this here epsilon 1 cannot be equal to epsilon 2 because of two different medias. Here epsilon 1 and epsilon 2 are two different media, so cannot be equal to epsilon 1 is not equivalent to epsilon 2. Therefore, D1t cannot be here. Epsilon 1 cannot be equal to epsilon 2, and therefore D1t cannot be equal to D2. So from this we can conclude that here electric field components are continuous across the boundary, but electric flux densities are not continuous across the boundary. These are the two boundary conditions related to the electric field component. Apply boundary conditions for the field blocks. Here, so we will take Maxwell's second. Next we will apply boundary conditions for the field blocks. Here we apply Maxwell's other equation, that is from the Gauss law, closed surface integral d dot ds is equal to q. Here when we consider field blocks, actually the Gauss law is, according to the Gauss law, the net flux leading through all the surfaces must be equal to the net charge enclosed within the surface. So here the net charge enclosed is q. So when we consider this one, it is symmetrically placed. So the charge, that is the flux leading from the sides, can be vanished because of the symmetricity. Only we consider only from the top as well as from the bottom. Here by applying boundary conditions to a field block, we can write, that is rho s equals to, and here this is the surface and the flux is leaving from this surface, so we can write this one as delta S d1, and here this is parallel to the normal component. Here similar process. Here also in medium 1 total fluxidence is decomposed into normal component as well as the tangential component, and medium 2 also second fluxidence 2 is also decomposed into normal as well as the tangential components. Here the tangential components will be removed because of the symmetricity, because it is seems equal in all directions. So tangential component of D will be vanished. Only normal component of D only exists here. So we consider d1n minus delta S d2n. So from this we can write d1n minus d2n into delta S equals to rho S. When rho S value is 0, if rho S is 0, means charge density at the interface is 0, then we can write d1n minus d2n into delta S equals to 0. Then delta S cannot be 0 because it is the area. Therefore, here delta S cannot be 0. Therefore, d1n minus d2n must be 0. From this we can conclude that, from this we can write d1n should be equal to d2n. Here that shows that describes that normal component of